My name is Nikhil. Today I would be showing my video on the topic of finite automata and other topics as well. Starting with finite automata, it is the simplest machine to recognize patterns. It is an abstract machine that has five tuples having a set of states and rules for moving from one state to another, which depends upon the applied input symbol. In simpler meaning, it is an abstract model of a digital computer. It consists of the following: Q, a finite set of states, and a sigma set of input symbols, a Q smaller one for initial states, a capital F for a set of final states, a delta for a transitions function. Finite automata is characterized in two types: DFA, deterministic finite automata, and NFA, non deterministic finite automata. In a DFA, machine goes in one state only for a particular input. Transition function is defined on every input symbol. Null or epsilon move is not allowed. For a particular pattern, there can be many possible DFAs. As shown in the figure here also, 0 to 1, 1 is the final state and it accepts 1 as an input only, going which after which it goes to 0, and the final state also has a 0. If the final state gets a 1, it goes back to 0 to return it until it gets finished at a 0. For the transition function for this one would be delta q into epsilon, sorry, q into sigma, that is capital Q. NFA is similar to a DFA, having few more features than that, but still those features don't add any power to NFA. And comparing both in terms of power, both are equivalent. The features are, of course, first, a null move is allowed in an NFA, and it can transmit to any number of states for a particular input. The transition function will be different for NFA because of the following exceptions: that q in delta q into sigma unions epsilon, that is null moves are allowed, and 2 raised to the power q, as shown in the figure. The 0 1 uh, 0 is the initial state and 1 is the final state. It gets 0 or 1 as an initial input, and if it's 0, it goes to final state also. For here also, it is like accepting both the values for 0, it can go any path over here. In NFA, if any path of input leads to the final state, then the input string is accepted. If number of states in an NFA is n, then its DFA can have maximum of 2 raised to the power n number of states. Now we would talk about the Ardens theorem. Ardens theorem is generally used to convert given infinite automata to a regular expression. It states that if P and Q are two regular expressions over sigma, and if P does not contain an epsilon null move, then the following equation in R is given by R equals Q plus RP, has a unique solution R equals QP. Meaning, whenever we get any equation in the form of R equals Q plus RP, then we can replace it with R equals QP. Ah, asterisk. For this, we have to prove the solution that it is valid, shown in this formulation behind. R equals Q plus RP for the first equation, which gives me, by replacing R by R equals QP, it gives me R equals Q plus QP in asterisk P. Taking Q as the common, I would get Q epsilon P, epsilon plus P into P. And then here I could prove that removing this Removing the remove after this, the epsilon will be removed because it is a null move and p is there only multiplied. So r equals qp. This would prove that r equals qp is the solution of r equals q plus rp. Now to prove that it is the only solution of the equation, we have the following ones, that taking the similar equation like r equals q plus rp, we go by replacing the r by q plus rp, and then we again replace it with the same one, and then we do that again. We do replace it by three times, and taking q as common, we would get we would get it r equals qp. This would prove that the solution is unique and ardens theorem is proved. So it is something that can be used. Pumping lemma, it is used as a proof for irregularity of any language, of a language. uh, it is the language is regular, it always satisfies pumping lemma. If the language is regular, it always satisfies pumping lemma. And is there one string from pumping which is not an L, then it surely isn't regular. Pumping lemma is defined for two types: regular language and context free languages. A regular language, for in a regular language, it states like, for any regular language L, there exists a V W which belongs to sigma, such that x is equals to uv w, and a modulus of uv is less than equals to n, and b modulus of v is greater than equal to 1, meaning that if a string v is pumped, the resultant string remains in L, as shown in like the diagram below, that when the v is pumped, the q always remains in the language. For a context free language, or CFL, it states that like, for any CFL, it is possible to find two substrings that can be pumped any number of times and still be in the same language. For L, we break its string into five parts and pump the second and the fourth substring. Pumping lemma is also used here as a tool to prove that language is not a CFL. If any one string does not satisfy the conditions, the language is not a CFL. Like in the diagram, if L is a CFL, there exists an integer n such that for all x belonging to L with modulus of x greater than equal to n, there exists UVWXY belonging to sigma, such that x is equals to UVWXY. And first, modulus of VWX is less than equals to n, and modulus of Vx is greater than equal to 1 for all I greater than 0, such that uv raised to the power I, wx raised to the power I, and y belongs to L language. Now we will discuss the Chomsky hierarchy. According to the hierarchy, grammar is divided into four types: type 0, type 1, type 2, and type 3. The unrestricted grammar, context sensitive grammar, context free grammar, and regular grammar. Type 0 includes all the formal grammar. These are recognized by Turing machines and known as recursively enumerable languages. For type 0, there is one thing that must be known, that at least there must be at least one variable on the left side of the production of type 0. A type 1 language generates type 1 grammar generates context sensitive languages, and the language generated by the grammar is recognized by a linear bound automata. uh, Type 1, there are things to be noted, that first of all, type 1 grammar should be a type 0, and the grammar production is in the form of alpha to beta. That is, the count of the symbol in alpha is less than or equal to beta. Type 2 generates context free languages, and the language generated is recognized by a push down automata. Here, the thing to be noted is that first of all, it should be a type 1 or a type 1 grammar, and secondly, the left hand side of the production can have only one variable and there is no restriction on the beta. Alpha should be 1. Then comes the type 3, which generates regular languages. These are exactly all the languages that can be accepted by a finite state automata. It is the most restricted form of grammar. There is another regular grammar called an extended regular grammar in this form, which extends to left regular grammar or right regular grammar. Now we discuss about generating regular expressions from finite automata. There are two ways to convert a finite automata into a regular expression. First, a state elimination method, and second is by using the Ardens theorem. In state elimination theorem, there are three steps to convert using state elimination method. First, we add a new non-accepting start state and an epsilon transition between the new start state and the former start state if the start state is an accepting state or has a transition in it. If there is more than one accepting state or if the single accepting state has transitions out, and add a new accepting state, make all the other states non-accepting and add a epsilon transition from each former accepting state to the new accepting state. For each non-start non-accepting state, in turn, eliminate the state and update the transitions accordingly. Uh, Now to convert and using Arden's theorem, we firstly converse conversion. We firstly have to assume first the transition diagram should not have any epsilon moves, and it must have only one initial state. Now, using the theorem to convert, we have two steps. Firstly, we create equations of the given form for all the states. Wij is the regular expression representing the set of labels of edges from Qi to Qj. The equations being Q1 is the initial state for this, being Q1 equals Q1 W11 11 and plus Q2 W21 and so on till Qn Wn1 plus epsilon. Q2 being similar but N2. Then we solve these equations to get the equation for Qi in terms of Wij, and that expression is the required solution where Qi is the final state. Thank you.